class we are discussing about protein precipitation method as one of the important downstream processing techniques used for separation of protein from fermentation broth or mix of different compounds present there, carbohydrates, lipids, DNA, RNA. It is a mixture milieu we want to separate out. Protein precipitation can be a very useful method just to minimize the volume of solvents we are dealing with, volume of slurry we are dealing with. Now, protein precipitation actually is to separate out the protein from the solution, either to eliminate the interfering agents or to purify them. So that is any one of these would be our objective of protein precipitation. Now, before that, we need to understand what is the how the protein is stabilized. So actually, water molecule around a protein stabilizes it. That is, this water molecule layer is known as hydration cell. So hydration cell is very important for stabilization of protein. You can see this is the hydration cell. So all the hydrophilic residues of the protein are facing together the water molecule. Hydrophobic core is inside the protein structure. Hydrophobic residues are buried inside. So that is the general stability perspective. Now when I am adding acid into a solution containing protein, what will happen? Acid is actually addition of acid is increasing hydrogen plus ion concentration. Those hydrogen plus ion concentration can be taken up by amino functionalized groups in protein. That means it is protonation will happen. So this protonation is actually positively charged to the protein surface, and hydration sphere is disrupted and protein can be precipitated if I am adding acid in a protein solution. So this phenomena is described here. You can see the positively charged ions is destabilizing the protein. Second aspect is about use of organic solvent, which is also used like alcohol and acetone. They actually reduces the hydration of the protein by removing water, so they replace water and they themselves surround the protein, which leads to causing aggregation and precipitation. So using of salt, you can see now water is thrown out from the hydration cell, but the solvent itself is coming into picture and they destabilizes the protein. And the last one option what we normally use or most often used is addition of salt, which is going to restrict the water molecule, taking out the water molecule from the hydrogen cell, and they are allowing more interaction of protein and protein in comparison to protein water. So protein interaction is increased compared to protein water, so it causes precipitation and aggregation. So this is the last approach. You see the water molecule has been retained by the addition of salt. Now most of the time if we add some salt initially, the globular protein solubility increases up to certain amount of salt, and this effect is termed as salting in. You need to understand why it happens. When you are adding salt, it is conferring some charge on the protein surface. So protein interaction is reduced. As the interaction is reduced, it is helping in solubilization. But at very high salt concentration, what happens? That we have already discussed in previous slide. So the second point, when you are increasing salt concentration, decreases the solubility. This is known as salting out effect. Most of the protein precipitation, as we really do in lab scale or industrial scale, precipitation perspective, it will be all salting out. And how the interaction is happening? The interaction can be disrupted depending on what methodology you want to adopt. So there can be three different interactions. One is protein water interaction through hydration between the charged side chain like asparagine, glutamine, lysine, hydrogen bonding between polar groups of the protein amino acid rather, like serine, threonine, tyrosine. This can be actually taking care of this perspective. And hydrophobic hydrations can be there, actually hydrophobic interaction rather, like phenine, alanine, valine, isoleucine. Those groups can be taking part in this process. And salt addition, how they are working? Actually, if I am adding salt, they increases surface tension, so hydrophobic interaction between protein is actually reduced, and the protein responds to the situation by decreasing its surface area. So they are actually removing out all the water, shrinking the exposed area, and they're making a new folding. That folded conformation is compact than the unfolded one, and this leads to precipitation of protein in many times. Now we'll be discussing about two particular type of salts. One is anti-chaotropic salt, which actually we use most often, like ammonium sulfate. What they do, they expose the hydrophobic patches on the protein by removing the highly structured water. So hydrophobic patches, when it is in solution, are covered with water, so they are actually not allowing the hydrophobic interaction to take place. But when I am adding the salt, they remove the water molecules, so hydrophobic patches becoming exposed, open. They interact with one another and cause precipitation. This is anti-chaotropic salts. The other one is chaotropic agents. That is chaos forming salt, rather I will say. So they actually, like urea and guanidine hydrochloride, they precipitate the protein by denaturing them, and these salt act by disrupting the hydrogen bonds and different kinds of hydrophobic interaction playing there. So the objective is totally different. One is breaking the hydrogen bond, hydrophobic interaction, and here they are actually allowing the hydrophobic interaction to take place. But in both the cases, protein get precipitated, and most of the time the solubility of the protein, actually as it is reduced in salt addition, can be variable depending on what kind of proteins we are dealing with. So essentially it is changing. Now we are showing here about salting out curve. With increasing salt addition, what happens to protein? This process is best given by Cohen equation, which is talking about a linear relationship of logarithm of protein solubility and the ionic strength of the solution. I, it is mostly linear. Beta and K are actually parameter or constant, which talks about what kind of protein we are dealing with, what is the salt. So beta is actually log of the solubility if the salting out curve is extrapolated to 0. So essentially you understand. So if there is I is 0, that means ln s equal to beta. So beta equal to ln s, the minimum solubility extrapolated from the graph. K are the characteristics constant of the protein in question and measure of the slope. So you can see the solubility graph of a particular example protein with ammonium sulfate. So this is percentage of saturation of ammonium sulfate, 10%, 20%, 40%, and here it is the solubility, logarithm of solubility. So one important aspect I will try to highlight here. If I am having a protein prepared in 26% saturation, those case the solubility of the protein expected is 1 milligram per ml. Very good. So for example, we have done some protein precipitation using 26% ammonium sulfate. So except this 1 milligram per ml, all other proteins molecule has been probably precipitated. Now if I change the salt concentration to 38% of saturation, so it is not a very big change, but you see how the solubility is going to change. So solubility initially was 1 milligram per ml, here solubility is becoming 0.01 milligram per ml. So 90% of the soluble proteins are now getting precipitated because solubility is reduced. So this way, actually from the solubility curve we can calculate how much salt we should add to precipitate out the protein. It can be used. We have also a chart for ammonium sulfate precipitation, which we normally use for our practical perspective. Now we'll be discussing about one problem and we'll clarify it. Assume we are talking about a solution. Solubility of protein is given 15 gram per liter at ammonium sulfate concentration of 2.2 molar, and solubility is 0.25 gram per liter when salt concentration is 3 molar. So two information is given, and question is calculate the solubility when the salt concentration is 3.8 molar. So how to deal with this kind of scenario? So here we already know that log S equal to beta minus Ki. This information is already known, and we can utilize the same expression for two way. First one is salt concentration 15, sorry, solubility 15. So log 15 equal to beta we don't know, k we don't know, and 2.2 is the salt concentration. We are multiplying with 3 because in our equation it is actually ionic strength. So what we are doing for ammonium sulfate, we are multiplying the concentration with 3 to get ionic strength. Why we are multiplying 3, that we will discuss after some time. And second case, the solubility of the protein is 0.25, beta we don't know, k we don't know, and 3 molar salt concentration. We are multiplying with 3 because I told you that for ammonium sulfate to convert salt concentration into ionic strength we have to multiply with 3. So that's why we are multiplying with 3 here. So I'm having now two equations, one is this one, another is this one, and we can solve both the equation because it is straightforward. This value is known, this is known. So beta k, two equation, two unknown, we can calculate k, we can calculate beta, and if we know beta and k, and our question is what is the solubility at 3.8 molar. So 3.8 molar means ionic strength is 3.8 into 3, 11.4. So we can actually calculate out what is the solubility. It is straightforward because beta is known, k is known, ionic strength is 11.4, so we can find out what is log s, and so solubility can be calculated. So I'm just leaving it out for you people to solve how this can be done. It is straightforward and simple. Now we'll be discussing why we are using this 3 multiplication and what is the general rule to calculate ionic strength from the salt concentration. Assume here P molar is ammonium sulfate. Now we are calculating, or we are asking you, so what is the concentration of ammonium? It is 2P because per mole of ammonium sulfate, ammonium 2, so 2 mole of ammonium will be generated. So 2P is the salt concentration of ammonium. Sulfate concentration will be P because ammonium sulfate only one sulfate, so it is P. And what about their charge? Charge is here 1, charge is here 2, and we know how to calculate ionic strength using this equation, which you normally use for charge species ionic strength calculation. So I is half of sum of all concentration of those ions, and Zi is the charge of individual ions we are discussing. So as we know, we can do the calculation over here. You see, as I told you, so ionic strength for P molar of ammonium sulfate, we are doing half of sum of 2P because ammonium concentration is 2P, I told you already, multiply 1 square because ammonium charge is 1. Now sulfate concentration is P and sulfate charge is 2, negative 2, so 2 square. So what is happening? 2P into 1 square and P into 2 square, so essentially 4P plus 2P, 6P, sum is 6P, divided by half is 3P. So essentially you understood, if the concentration of ammonium sulfate is P molar, the ionic strength will be 3P. That means we are simply multiplying with 3. If we have done it for P molar, we can do it for any number of mole, 3 mole, 4 mole, 5 mole. It will be 3 times of the salt concentration will be the ionic strength. So we understand how, using the information of salt concentration and solubility data, we can also predict the solubility of protein at a different or unknown salt concentration.